This video deals with a very specific application of continuous decay called the half-life problem. Now, before we get too far into an actual example, I want to first make sure we're all on the same page as to what half-life is. A half-life is just the time it takes for half of the mass of a substance to break down or turn into another substance as it decays away. So for example, carbon-14 is a radioactive element that has a half-life of 5,730 years. So that means half of it goes away every 5,730 years. Let's look at an example. If at the beginning we had 100 grams of carbon-14, that would mean 5,730 years later, we would only now have 50 grams. We'd have half as much. After another 5,730 years, or after 11,460 total years, we would have only 25 grams. Another 5,730 years later, or 17,190 total, we would have 12.5 grams. And you can kind of see where this is going. One more time, another 5,730. We would only have 6.25 grams left. So this is what half-life means. It's how long it takes in order for half of the substance to break down each time. So what does it actually look like in a problem? Well, here is an example. Carbon-14 is often used in carbon dating. This is a way that scientists determine how old relatively old specimens are, such as fossils. They look at how much carbon-14 is left inside of the specimen, because carbon-14 breaks down over time. So the older something is, the less carbon-14 there is left. So we want to know how old is a fossil if it contains only 15% of its original carbon-14. Now there are actually, in this case, two parts to this problem, because there are two pieces we don't know. We don't know the rate of decay, R, and we also don't know how long it takes, because that's our final question. So that means we actually have to figure out both those pieces separately. First, we're going to find R. Now, R in these half-life problems will depend only on the element you're measuring. So this depends on the fact that it's carbon-14, not the specific fossil. So this only depends on the half-life. In this case, the half-life of carbon-14. Now, you might be thinking, well, we don't know the starting amount, and we also don't know the final amount, but it's not important exactly what they are, because again, this is just about the half-life, not about any specific substance, or not about any specific specimen. So what we can do is just pick some easy numbers. I always like to just do 1 as my starting amount, and I like to use, since it's half-life, that means after one half-life we would have 1/2, because that's half of 1. We don't know what R is, that's what we're trying to solve for. But we do know how long it takes to get from 1 gram of carbon-14 to half of a gram. We know that it takes 5,730 years, because that's how long a half-life is. So now we only have our one variable to solve for. Well, right away you can tell that this 1 right here doesn't really mean anything. We can divide away the 1 and it's just completely gone. So our problem is actually this: 1/2 equals E to the 5,730 R. So just like in our last video, this is now a relatively simple exponential equation. We can solve this, since our exponential is isolated, by taking the natural log of both sides. So the natural log of 1/2 equals the natural log of E to the 5,730 R. Natural log and E cancel each other out, giving us natural log of 1/2 equals 5,730 R. And then we can finally solve for R by dividing both sides by 5,730. So R is equal to the natural log of 1/2 over 5,730, which comes out to about negative 0.000121. Now, hopefully it makes sense that R is negative because this is a decay process, right? We have less mass over time. So now that we have this value, that's the first thing we had to find. Because we can now use this to finish solving our actual question, which is what is T, right? That's what we're really looking for. How old is this fossil? So now let's go back to filling in the pieces we know. Well, they only tell us that we have 15% of what we started with. They don't tell us what we started and ended with, so let's just pick some easy numbers. Specifically, Eilish always, again, like to say, well, let's start with 1 gram, and that means we would end with 15% of that is 0.15 grams. So we can fill in the rest of this. E, we now know R is negative 0.00012, and we don't know what T is. Again, this 1 doesn't really mean anything, so we can divide it away or just ignore it, and we really are solving this problem. So to go from here, this is just a basic exponential equation. We're going to take the natural log of both sides. Oops, I lost my 1 up here. 121 T. And again, natural log and e to the x are inverses, so they cancel each other out, leaving us with natural log of 0.15 equals negative 0.000121 T. And we can just finally divide away that negative 0.000121, giving us T equals the natural log of 0.15 over negative 0.000121. This goes into your calculator, and you get that T is about 15,679 years. Meaning that our fossil is 15,679 years old.